Let's start. All the positive integral powers of a symmetric matrix are symmetric. So we will take positive integral powers of a symmetric matrix and we need to show that those are also symmetric. Okay, so have a look at this property. All positive integral powers of symmetric matrix are symmetric. So let us prove this particular fact. Okay, let A be any symmetric matrix. So we are assuming that A is any symmetric matrix. So by definition, what do we have? A transpose is equal to A. Okay, if A is symmetric, then A transpose will be equal to A. Okay. Now let us assume this is equation 1. Let us assume this is equation 1. Let M be positive integers. Okay. Let M represent positive integers. Okay. So this small m represents positive integers. Now, by the definition of powers, by the definition of indices powers, you know that a to the power m, a to the power capital A to the power small m implies that capital A will be multiplied m times. Capital A will be multiplied m times. Okay. If we are able to show capital A will be multiplied small m times, that is the meaning of a to the power m. Capital A will be multiplied, matrix capital A will be multiplied small m times. Okay, that is the meaning of a to the power capital A to the power small m. Okay, and m is positive integer. Okay, so a square is equal to what? A multiplied by a. Okay, a cube is equal to what? A cube is equal to a multiplied by a multiplied by a. Okay, similarly a to the power m will imply that a multiplied m times. Okay, if we are able to prove, if we are able to prove that a to the power m transpose, a to the power m whole transpose is equal to, if we are able to prove this, that a to the power m whole transpose is equal to a to the power m, if we are able to prove this in case, then if we are able to prove this, then what will it imply? It will imply that a to the power m is symmetric. Okay, it will imply that a to the power m is symmetric. This will be the conclusion. So we need to prove this particular fact because it is asking us to prove this. A to the power m is symmetric. That means that a to the power m whole transpose should be equal to a to the power m whole transpose should be equal to a to the power m. Okay, so only then a to the power m will be symmetric. So we need to show this thing. Now let A be any symmetric matrix. Let us erase and let us have a look. Okay, let A be any symmetric matrix. So A is symmetric, we have assumed. So A transpose will be equal to A. Now M is a set of positive integers. So A to the power capital A to the power small m transpose will be equal to A multiplied m times whole transpose, complete transpose. Now we already know this property that AB whole transpose, AB complete transpose, AB product complete transpose is equal to B transpose A transpose. AB complete transpose is equal to B transpose A transpose. So applying that property, this A will come here, the second last A will come here, this first A will go here. Okay, but they are identical because all of them are A itself. Okay, all of them are A itself. So it will be A transpose multiplied by A transpose multiplied by A transpose multiplied by A transpose. How many times? M times. M times. A transpose will be multiplied M times. Okay. Now we already know that A transpose is equal to A. From this equation 1, we already know that A transpose is equal to A. Okay. So this A transpose will be equal to this A. This A transpose will be equal to this A. This A transpose will be equal to this A by this particular definition of symmetric matrix. Okay, because A is symmetric. So A transpose will be equal to A. Now A transpose is M times. So A will also be M times. So A multiplied by A multiplied by A, how many times? M times. Okay, small m times. Small m is a positive integer here. Small m is a positive integer here. So capital A multiplied by capital A multiplied by capital A, how many times? M times. Okay. So this is clearly equal to a to the power small m, capital A to the power small m, capital A to the power small m by definition. By definition, when we multiply something m times, then it is that quantity to the power m. When we multiply something m times, then it is that quantity to the power m. Okay, by definition of indices. So capital A to the power m we have successfully shown. So we started with a to the power m whole transpose, a to the power m whole transpose, we started with this. Okay, and we have ended at a to the power m. So a to the power m complete transpose a to the power m complete transpose is equal to a to the power m. We have successfully shown. And m is what? M is a set of natural numbers here. M belongs to this small m. Small m belongs to capital N. Small m belongs to capital N. Okay. Small m belongs to capital N, where capital N is a set of natural numbers. Now what is a set of natural numbers? 1, 2, 3, 4, 5, 6. This is a set of natural numbers. 0 is not included in set of natural numbers. It is saying positive integers. So positive integers are natural numbers. Positive integers are natural numbers. 0 is not included. 0 is not included. So positive set of natural numbers. Positive integers means set of natural numbers. Positive integer simply means that set of natural number. Now what is set of natural number? Set of natural number means that 1, 2, 3, 4, 5, 6, 1000, 10,000 like that. Full figures. Okay. So this is the meaning of natural number. This is the set representing natural number. Now as a to the power m whole transpose, a to the power m whole transpose is equal to a to the power m. So clearly a to the power m is symmetric matrix. Clearly a to the power m is symmetric matrix by definition. By definition of symmetric matrix. Whenever a matrix satisfies this condition, it is symmetric matrix. So a to the power m is symmetric matrix. So we have successfully shown this particular thing.